Good morning, good afternoon, good evening, depending on wherever you're watching this from. Welcome to Weekly Science Review conducted by Vetri Labs. So we take a paper that's published in the field of electrochemical science, engineering, material science. Typically, we select a paper that's in open access mode and do the discussion. Professionals from all over the world take a lead in presenting the paper. After that, we have an open Q&A and discuss the topic. Today's session is going to be led by Dr. Hari Gopi. Hari, over to you.
So thank you, Shok, and thank you for the given opportunity. Is it audible, my voice?
Yes.
Okay, yeah. So I thank Dr. Chok and Vetri Labs for giving me the opportunity to discuss this paper regarding to membrane ionization membrane for asymmetric cycling of VRFB. Sorry. So the advantage of redox flow battery is that we can scale from small power application to larger level, large power from 1 milliwatt to 1 megawatt level. We can scale up this kind of redox flow batteries, and also the maintenance cost, long lifetime. So lot of advantages we have with the redox flow batteries. Since we are using same element species, that is a vanadium, which is obviously at different oxidation state, but we are using the vanadium on both sides of the system, so the contamination of electrolytes is avoided. So generally, the if you take a VLFB system, the capital cost is charged for mostly with respect to the electrolyte, vanadium based electrolyte 40%, stack 35%, and the remaining DOP components 25%. In the stack component, it is still subdivided into membrane, bipolar plate, and electrodes, etc. So coming to the membrane part, Nafion has been used as a membrane in redox flow batteries. So even though Nafion is a benchmark based on lot of advantages it has in chemical and mechanical stability because of its PTFE backbone and high conductivity because of the pattern sulfonic acid groups. So some limitation we have with Nafion is that it impedes in cost factor and also the ion selectivity. That means the Nafion will work as a hydrated mode. So the way along with the water, vanadium crossing over to the other side is also possible, which leads to capacity fading. So the advantages of going with anion exchange membrane over cation exchange membrane is that the vanadium ion cannot go to the other side as because of the same charge, that is the Donan exclusion effect. Thereby the vanadium crossover is reduced, resulting in high Coulombic efficiency and long self-discharge duration. And also the oxidation stability is also improved. So what is Donan exclusion is effect is that, so this is consider this as a PEM and consider this as an AEM. So in PEM, the transfer of vanadium plus to the water is easy. We can able to see the because it's a protonic mode, so the chances of the vanadium crossovering is easy. Whereas in the anion, if you come to the anion side, the movement of the vanadium ion towards the other side is difficult because we will be having only the anion traveling through the membrane. So that is the Donan exclusion effort. The in anion exchange membrane, the quaternary ammonium groups prevent the cations to go through the membrane. Like vanadium ions, it prevents to go through the membrane. So this has an effect in the Coulombic efficiency and also enhancing the Coulombic efficiency and also prolonging the self discharge. So this paper, they used polyphenol based backbone to develop anion exchange membrane, and also they say a concept to minimize the crossover. They say a concept of asymmetric volume. So which is that they don't take equal volume of anolyte and catholyte solution. So some reduction will be there. I will be showing in the next slide. So they say some asymmetric volume helps in the improvement of coulombic efficiency as well as your discharge rate. And that's what it minimizes your capacity fading. So this is the preparation they followed. The first step is the precursor. They wanted to prepare this precursor. So the precursor is prepared by an superacid catalyzed hydroxyl alkylation. That means arene like phenyl rings react with hydrogen containing carbonyl compound to give a hydroxyl alkyl product. That is the reaction. So these are the chemicals they used: the piperidone, terphenyl, and trichloroacetophenone. So they all mixed, and then at 0 degrees centigrade they added the acid catalyst, trimethane sulfonic acid, trifluoroacetic acid. So and they continued at 0 degrees centigrade for 24 hours. So after the completion of reaction, they precipitated using ethanol, and the polymer powder is washed with several times with water and potassium carbonate. So in the second step, this whatever dried polymer, so they quaternize it using the iodomethane, and we will get a and it was still overnight, and then precipitated in isopropyl. We'll get a yellowish powder, which is then filtered, washed, and used for membrane fabrication. So whatever this yellowish powder was dissolved in DMSO to make a 5% solution, and that solution is filtered through a Teflon filter to remove any impurities kind of thing, so that we will have a good membrane. And they dried it at 85 degrees centigrade for 48 hours, and they exchange with the chloride form by dipping in 1 molar NaCl. So they use both forms, iodide form and chloride form. And coming to the characterization, they characterize by specific ASR and ionic conductivity. Both actually they compared PEM and AEM. So they compared in every aspects of PEM and AEM, area specific resistance, permeability, oxidation stability. So they went into hand with the Nafion and compared. So these are the experimental parameters they used, dipping in a 2 molar sulfuric acid, and then before and after they measured the EAS with membrane and without the membrane, and then they calculated the ACR, and then from the ACR they calculated the conductivity. The permeability, the permeability of VO2 plus is they say it's robust because it's towards oxidation. It's very favorable. So they wanted to study the permeability. Permeability of this what Nafion and this synthesized membrane for the this vanadium oxide permeability. So they have a permeation cell. So they take a membrane piece of 8.3 centimeter square between a two electrolyte chamber. They maybe I can show you. So this is the diffusion cell they use. So one side they fill with vanadium sulfate, and other side they fill with the magnesium sulfate. So this is the place for keeping the membrane. The membrane area is 5 centimeter square, and yeah, left chamber is filled with vanadium sulfate, and this is with respect to permeability. Oxidation stability they studied by immersing in 1 molar vanadium oxide solution in sulfuric acid, and then they measured the change in how it is varying with respect to the oxidation stability. And the charge discharge cycles was conducted using electrochemical cell, which consists of graphite plates with the serpentine flow field. They used a gasket of 1 mm for sealing, and then they used just as carbon papers as electrodes. And they say they pre-treated the electrodes at 5 degrees centigrade for 3 hours. And for the symmetric cycling, they used 20 ml of vanadium electrolytes on both negative and positive sides. For asymmetric test, depending upon the which membrane they use, it will be reduced by 25%. And then the electrolytes were purged with the nitrogen for 10 minutes so that the oxidation of energy is not happening. And then they the electrolytes were circulated at 40 ml per minute using a peristaltic pump, and they investigated the performance from starting from current density 70 to 200 milliamps per centimeter square, and they returned to 70 milliamps per square and checked the is there any capacity degradation. So they checked that, and so coming to the so this is the synthesis part. So this is the terphenyl, and this is piperidone, and this one is trifluoroacetophenone. So they polymerized it using this acid, superacid, and then this is the coordination step. So this they confirmed using the NMR spectroscopy. So this around 7.5 ppm corresponds to the aromatic proton, and this 3 ppm and 2.5 ppm is corresponding to the methyl and methylene of this piperidone group. So the methyl proton will come at around 2.8 ppm, and the methylene is around at 3.4 ppm. So they confirmed the structure using the NMR spectroscopy. As I was mentioning, they measured the permeability, water uptake, and radio resistance in comparison to Nafion. So they took the same kind of a thickness of membrane, and then they measured this conductivity, uptake, and permeability. So this is regarding to the chemical synthesis and its confirmation. So as I mentioned, they use this permeation cell. So they carried this experiment for 140 hours, and they say is that the vanadium permeation is very less compared to Nafion, even after 140 hours. So not much difference is there in the concentration of vanadium, but when compared to Nafion, there is a slight change in the concentration of Nafion, and they this one similarly they considered they characterize the oxidation stability at three different membranes: Nafion, and this synthesized membrane at RT, and synthesized membrane at 30 degrees centigrade. So they say as Nafion has a fluorosulfonic backbone, PTFE backbone, it is very oxidation resistant. So not much variation in the concentration they are evaluating. And with respect to PPT at room temperature, slight difference is there. Slight difference in this slight reduction is there, but not much major difference even after 400 hours. But when they increase the temperature to 30, so the 3 times more VO2 plus is generated. They say it's because of the iodide, whatever is there in the membrane, it reacts with this VO2 plus, so that they say because of that the concentration is increasing and the oxidation stability is lost. So this is the results of symmetric cycling and asymmetric cycling for Nafion and the synthesized membrane. So the Nafion symmetric cycling, they have a Coulombic efficiency of around 93%. Though there is a slight there is a slight increase with respect to asymmetric cycling for Nafion. For the symmetric cycling, the started with 20 and it is around ending at around 16. So there is a 20% capacity fade. So they say it's because of the crossover of active species. In Nafion, the permeability of vanadium 2 plus and 3 plus is more compared to the positive side of VO2 plus and VO2 plus. So because of that, the diffusion, they say it's happening from the negative to the positive side, and the apart from this is with respect to the vanadium diffusion, but with respect to the current conduction, the net vanadium and water transfer under migration is from the positive to the negative side during charging and negative to the positive side during discharging. So they say because of this phenomenon, there is an increase in the volume of 7% on the positive side, and they attribute to this increase of the volume to these reactions So this, because of this kind of reaction, they say the volume might be increased on the other side. Similarly, it's so they say it's from the above, it's obvious that the negative electrolyte limits the capacity for this vanadium flow in with respect to Nafion. So they say 25% excess volume was used on the negative side to hinder the capacity fade. So coming to this our synthesized PPT synthesized cycling studies. So the symmetric measurement achieved a Coulombic efficiency of 94%, which is higher than Nafion, and the permeability of this ion from the positive to the negative is happening on the anion exchange side. And the 7% volume increase is happening on the negative electrolyte because of this diffusion. And so for this kind of AEM, they use 25% excess volume on the positive side of things. And this is a graph of energy efficiency compared with Nafion and PTPT. So the not much variation in the energy efficiency is there for symmetric and asymmetric cycling, whereas for the synthesized PT membrane, so a predominant increase was there in the energy efficiency. And okay, this is with so they also studied the long-term studies of asymmetric cycling, and they say a capacity of around 4% was there, and even though they say 4% loss was there, they claim that there's no change in the chemical structure of the polymer membrane before and after cycling. They have done the NMR studies, Raman studies to confirm that claim that no change in the chemical structure has taken place. But some kind of fading is happening, which they ascertain to the whatever that iodide in the membrane, it is contaminating, which is reacting with the membrane and contaminating, which could reduce the conductivity of the polymeric anion exchange membrane. So that's they relate to this 4% loss. And then okay, so before discharge, before this VRB cycling, the membrane was in yellowish color. So after this asymmetric cycling, it was changed to red color. And they say it's because of due to the iodide oxidation and complex formation. So what they did was they immersed this red color membrane in 3M sulfuric acid, and they can able to retain whatever the previous color of the membrane. So this is with respect to the efficiency of before immersing in the sulfuric acid and after immersing in the sulfuric acid. So not change in the Coulombic efficiency, but they say there is a increase in the voltage efficiency with respect to the before and after dipping in sulfuric acid, which they claim, which they pertains to the that iodide oxidation, which is mitigating. That's what they claim. So what they did is that they wanted to confirm this iodide is reducing the conductivity. So they carried out the same kind of studies in chloride form, and they found that the chloride form PPTD has higher discharge capacity and very good higher voltage efficiency. So they say this iodide is only detrimental to the conductivity of PPT. So they say this, instead of using iodide, if you go for chloride form, it will increase in your voltage efficiency. So nano membrane, the terminal backbone and piperidine functional groups were synthesized. The membrane exhibited lower vanadium permeability than Nafion 12, and also oxidation stability as equal to of Nafion 2 and 2. The electrolyte imbalance during VSB cycling was overcome by using asymmetric electrolyte volume, which significantly reduces the capacity loss. And as mentioned, the presence of iodide contributed the reduced ionic conductivity and reduced voltage efficiency. which they claim, which they confirmed with repeating the experiment in closed form. So thank you all.
Excellent. Thank you very much, Hari. That was very nice summary of the paper. Now let's open it up for question and answers and comments and thoughts. Any questions, comments, thoughts?
Yeah, I have 3 questions. Hari, can we go to few slides back? Yeah, still more. Yeah, still. Yeah, here the
Sorry.
no problem. A bit back. Previous polarization curve. Yeah. If you see here the PT, this graph D,
Yes.
the
Yeah.
performance is much higher than the Nafion 112.
Yes.
And if we go back to the slide, which has a table.
Table.
Yeah, back.
Okay.
Back. Yeah, here. And the ASR value is around 0.53 ohm centimeter square.
Yeah.
Here, the conductivity of PTPT is much lower, but the ASR value is a bit higher. Did they give any comment on it? How it has come
Sorry,
higher value?
No, sorry, Ramesh, sorry to interrupt. If you go back to that chart, D chart, the curve, yeah, this particular one I see as open circuit voltage, which talks about the intermixing of the electrolyte,
Okay.
not the performance, right? It's OCV versus.
Okay. Got confused. Okay, fine.
Yeah, it's not the performance of the capacity draw. It's more just we're looking at open circuit. That's my understanding. Is that correct, Harry?
Yes, sir. They wanted to that, as I mentioned, the self-discharge study. So they keep at some potential current density, and they see how how close, how fast are it comes to zero.
Correct.
Yeah.
Yeah,
So
this
that
talks
is a kind
about
of a self-discharge study.
Correct, intermixing. So essentially, they are proving that the AEM rejects the cation very well, and hence retains the capacity.
Yeah, okay, sure. Thanks, Chuck, for the clarification. And regarding the asymmetric configuration, may I know what kind of electrolyte they used in the counterpart?
No, same electrolyte.
It's volume change. When they
volume
say
change.
It's
volume
okay.
change.
Yeah.
Okay, they want to increase the charge balance on the other side to have a better increase in efficiency.
Because of this permeation happening, so they say that volume increase will help to reduce the fading effect.
Okay. Fine. And the third one, which is a bit confusing for me, I don't understand. They used iodide-based ion exchange membrane. And what kind of ions is transferring between these two compartments?
No, I did not get it. What?
No, the ion transferring between one compartment to other compartment. Is it OH ions or the vanadium ions?
No, vanadium only. It's not OH. It's not OH.
It will be the sulfate. If it's vanadium sulfate, if it's a AEM anion exchange, it will be the sulfate ion that gets transported, right?
But AEM does not cannot hold the sulfate ions. Okay, yes, correct. It's also an anion, correct. Yeah.
Right.
Yeah. Thank you, Chuck. Yeah. I am not thought of that angle.
Yeah. Yeah, it will not be vanadium because it's vanadium VO2 plus it's cationic, so it has to be anionic. Sulfate will be because it's vanadium sulfate is used as the electrolyte.
Okay. Yes.
Yeah.
Thanks, Hari. It's a nice paper and very good work.
Yeah.
Yeah, thank you, Amish.
Any other questions, comments, thoughts? If not, let's close the recorded session of this. Thank you all for joining. We meet weekly on Saturdays, 10 a.m. Pacific time, 10:30 p.m. IST. And you can also present your paper, take an open access paper and lead the discussion. Please send us an email, info@vetrilabs.com. That email again, info@vetrilabs.com. Thank you and have a safe and good week ahead.
Thank you.
Thank you all.